to find the transfer function V out over V in, the best way to do this is that notice that we have an inverting op-amp configuration and we have two impedances, one Z in and one ZF. Then we know from theory that V out over V in will be equal to minus ZF over Z in. We could also go ahead and do KCLs and KVLs over here. It would be fine, but this is the fastest and best way and more efficient to do this. Now, how much is ZF? R2 in parallel to C2. How much is Z in? C1 plus R1 in series. Now the impedance of the capacitor is 1 over CS. In this example C2 and this C1. So we go ahead and try to find a good expression. But then the next step we're going to take is we're going to eliminate this frequency from these individual small fractions. So we're going to multiply these with C2S. So C2S, C2S, and this with C1S, C1S. So this whole thing will become the following. Now, from this expression, we can go ahead and try to do the rest of the exercise, but the best way to proceed from here is to express these as fractions. So now from this point onwards, the next thing that we're going to do is to express these factors as a fraction. So we have something like this. I expressed these as a fraction. Now, I know that these things are frequencies. Why? Because I divide the frequency with something which is the same as multiplying it like this with this frequency. And this whole fraction must give me a constant number, V out over V in. It must not have an expression of something else. Therefore, by the way, this is the transfer function, alright? Now I'm ready to try and draw the transfer function in respect to frequency. I will use absolute values just so we can keep things simple. And then I'm going to, first of all, put all of my frequencies that I know and are relevant in this on this plane. So one frequency that's relevant is 1 over C2R2. One other is 1 over C1R1. I know that this is much higher than this, so I will put 1 over C1R1 over here, and I will put 1 over C2R2 over here. Okay, do we have another frequency? Not really, that we know. So let's go ahead and try and solve it. Now, the first thing that we do here is to say, we'll start with smaller frequencies. So, what if this frequency was very close to 0 and much smaller than 1 over C1R1? What would happen then? Well, this would be much smaller than this. So this over this would give us practically 0. So let me use another pen over here. So S over this frequency would reduce to 0, plus 1. This over this frequency would also reduce to 0. Now how about this? Well, this frequency will be multiplied with R2C1. And that tells me the following. This V out over V in will have a behavior of something multiplied by S, by the frequency. So we're going to have something like S starts from, let's say, close to 0. So the transfer function will start from here. Up until it is comparable to this C1R1, it will reach a value it will increase, as you see here, and then something else will happen. So this whole thing will increase somehow, perhaps something like this. Now, how much will this value be? Well, let's see. It goes up and up and up until one point, when this frequency becomes comparable to 1 over C1R1. And then, when this frequency becomes, let's say, 10 times higher than 1 over C1R1, this whole term becomes much, much larger than this term, than this plus 1. So this plus 1 gets overwhelmed and eliminated. Again, over here, the same, because the frequency is much, much smaller than 1 over C2R2, this whole thing is 0, like before. So this is plus 1. Let me write this again so you can see it more clearly. It will be reduced to something like this. This frequency gets simplified with this frequency, and this whole thing gives us A. And if we do the math here, it will be that R2 times R1 times C1 squared, with a minus in front, but we are working here with absolute values, so we don't really care about it. So that tells me that this transfer function now must have something like a constant value. So from 10 times here onwards, it will have a constant value. Let me write again. Have something like a constant value up until some point. And now I will just connect these approximately. This is an approximation. We want here to study the behavior of the circuit, so approximately, so it's okay to do these things for now. This value will be how much? R2 C1 squared R1. This value will be constant, so this is constant up until a point. What is the point? Where the frequency becomes comparable to C2R2. So let me erase again. Now this frequency comes close to this, and then becomes 10 times at least higher than this. So this term completely overwhelms this plus 1, very soon 10 or 100 times higher frequency. Again, like previously, this whole term overwhelms this plus 1, and this whole expression reduces now to this. Now I can simplify the frequencies. I can say, let's see, this R2 will be simplified with this R2, because we will multiply this over here. This will be multiplied over here, so this C1 also simplifies with this C1. Therefore, this whole thing gives us the following. R1 C2 over S. Now this means that this transfer function from that point onwards, from some point over here, now I expect this function to become lower before we reach this point, because this becomes comparable. Alright, so we divide by something extra. So I expect it to go somewhere lower over here. And from that point onwards, we have something like this. The value of the transfer function getting smaller and smaller and smaller as frequency increases. And then we will connect it in a way something like this. And now we can make some observations. From this point, from 0 up until somewhere close to 1 over C1R1, this whole thing behaves like a differentiating amplifier. It performs the mathematical operation of differentiation from this point upwards, up until one point. Then, from this point all the way to here is a band pass filter between these two frequencies. And then, somewhere higher than this frequency, let's say 10 times and onwards, this whole thing behaves as an op-amp integrator. Now, for a more in-depth analysis, you can check out what I've prepared for you in the description below, or you can check out the other videos I have done in this channel that we cover the differentiator op-amp and the integrator op-amp in much, much more detail. Alright, that was it for today. Study well and take care. Goodbye.